Hello and welcome back. Today in calculus, we will talk about the special cases. Day two of partial fractions. Last time we talked about partial fraction as like a basic idea as to how to actually use it, and then afterward how to use it in terms of integration. So now we're going to look at the special cases of partial fractions, meaning like, what happens if you have factors that are not linear, or what happens if you have factors that are maybe repeating. So this is what today is going to be about. Okay, so here is going to be, there are a total of two special cases, so it's not too bad. But this is something that we should actually consider though. So the first part is that the factor in the numerator is 1 degree smaller than the prime factor that is in the denominator when you are using any kind of partial fraction. So this is something that we did not mention in last time, and then this is something that we need to, basically kind of say just in case what happens if you have something like, say, a factor that's quadratic. So here you can see in our example below, we have 1 divided by x cubed minus 8. Now, according to difference of cube, factoring again in algebra 2, x cubed minus 8 gives you x minus 2 as one of the factor, and then the other factor is supposed to be equal to x squared plus 2x plus 4. So that's using the difference of cube. Now, in the numerator of the x minus 2, that is just going to be a, just like last time, because of what we just said in the previous video. But the special case is now for the factor of where you have x squared plus 2x plus 4, the numerator, you'll notice that there is a difference. It is actually bx plus c. And for that, and that's basically what I was trying to reiterate over here earlier, that because the factor in the bottom over here is quadratic, then that means that the factor on top has to be 1 degree smaller, hence that's why it's linear. Whereas over here in the first factor, the denominator is a linear factor, so then 1 less degree is going to be a single constant. So that's where the a is actually coming from. So meaning if you have a factor that is x cubed, then that means that the numerator, you would have to have some sort of ax squared plus bx plus c, which is a quadratic then in this case, and so on and so on and so on. And for each one of those, you need to make the specific or corresponding amount of coefficients for it. So that's why you have bx plus c, and then so on and so on and so on. But anyhow, to solve for this, it's basically the same thing as before. What we're going to do is we're going to try to solve for a, b, and c by using one of two methods. Now, this is one method that we did not talk about last time, which is the following. Well, first off, what I'm going to do is I'm going to go ahead and take this guy right here, and I am going to simplify that equation by multiplying to both top and bottom, and multiplying to both left and right by the factor, which is going to be x minus 2 times x squared plus 2x plus 4. And my pen's a little bit slower, but it's slowly catching up, and there you go, which is actually the same thing as x cubed minus 8. So multiplying that to both sides, that will get rid of all of my denominators. And this is what you're going to get over here on the bottom of it. So let me just kind of highlight that so you guys can all see it a little bit better. And let me go ahead and make this a little bit thicker. So that's this guy right here. Okay. Now, what we're going to do is on the right-hand side, last video, I said, hey, don't multiply this out on the right-hand side because it's actually nice in factored form. But in this option right here, which is going to be called the system of equation, I'm going to show you what happens if you multiply it out. If you multiply it out on the right-hand side, this is what you're going to get on the right-hand side, which you can see is not exactly that nice. But I've also color-coded the terms that are actually going to be alike. So for example, you'll notice that we have x squared terms, which is going to be a x squared and then plus bx squared. Then you also have the first degree terms that we can kind of put together, which will be 2ax, and then we also have negative 2bx, and then we also have cx, so we can group those together. And finally, for the last one, we'll be looking at the single terms, which are, 0 degree terms, which will be 4a, and then we'll have negative 2c. Now, grouping all the terms together, this is what we have now underneath, which is 1 is equal to all that over here on the right-hand side. So here's what I want you to notice. On the left-hand side, it's just a plain old 1, nothing special about it. There are no x squared terms. So what that means is for this factor where the coefficient is a plus b, I can set that equal to 0 because, again, on the left-hand side, there's no x squared terms, so the coefficient is equal to 0. Similarly, the 2a minus 2b plus c also has to be equal to 0 because there are no first degree x terms. So that's where this guy over here comes from. And then finally, for the last part, 4a minus 2c, that is going to be equal to 1 because that's the only part that's going to give you a single coefficient without x. So that's where the 1 is equal to 4a minus 2c comes from. And as a result, you can see now because we have 3 equations and 3 unknown, then that means we can solve for this system of equation. And I took the liberty of solving for it quickly over here. So if you want to solve it, pause the video and solve for each one, by all means, okay? And don't worry about it. I did check just to make sure that it all works out. And yeah, it actually comes out to be that then. So this is basically what happens if you multiply everything out and you can do a system of equation to solve for a, b, and c. So in the end, you can get exactly the same thing. Now, that's option number 1. Option number 2 is using what we did in the last video, which is to say, hey, this whole thing right here is going to be first, according to my rules of partial fraction, equal to this guy. Then, just like before, I'm going to go ahead and multiply out, so then that way we don't have a denominator. And I think in this part, what's best is we just go ahead and choose values of x to plug in so we can see what a and b are equal to. Now, since if you look at my previous example, you have a denominator of 12, which is the LCM in this case, I'm going to make my life a little bit easier by saying that let's go ahead and take our partial fraction and make it so that it's a little bit different. So it's going to be 12 divided by x cubed minus 8 instead of 1 divided by x cubed minus 8. But, you know, it's the same idea, but except you're just not going to get fractions for your answers. So anyhow, going back to this part over here, I'm going to go ahead and say let x equal to some number. Well, the easiest number I can think of is over here. If you notice, we have an x minus 2 as a factor. So why don't we let x equal to 2? Whatever allows me to diminish some of those terms. So then that means that 12 is equal to a multiplied by 4 plus 4 plus 4, and then plus, well, the other factor is going to be b times 0 plus c multiplied by 0. So all of that is going to cancel out. So I'm looking at 12 is equal to a times 12. So that means that a is equal to 1. So similarly, let's go ahead and choose something else then. Let's say this time, why don't we go ahead and let x equal to 0, because I noticed that over here, that's going to get rid of this b term. So if x is equal to 0, then we're going to get 12 is equal to a multiplied by 0 plus 4, and then plus the 0 over here for b, and then plus c multiplied by negative 2. So clean that up a little bit more. We get 12 is equal to 4a, and then we have minus 2c, and if you remember, we solved for a already, so we can actually plug that in. So 12 is equal to 4 minus 2c, and then we have 8 is equal to negative 2c, so that means that c is equal to negative 4. And finally, we're going to go ahead and choose another value of x. At this point, we don't have any like diminishing terms, diminishing factors we can use. So we could just use any value of x we want. So easiest one I can think of besides 0, because we already used it, we're going to go ahead and use like 1, for example. So now 12 is equal to a multiplied by 1 plus 2 plus 4, and then plus b plus c, and then multiplied by negative 1. And once again, we solved for a and c already, so we can go ahead and plug it in. So 12 is equal to a multiplied by 7, and then plus, actually a we solved for, so why don't we go ahead and plug that in right now. So a, which is equal to 1, I'm going to go ahead and throw that in there. And then b minus c, or b plus c, so that's going to be b minus 4 multiplied by negative 1. So let's see, move the 7 over to the other side, so that's 5 is equal to let's see, 4 minus b, if I'm looking at it correctly. So if I move b over to the other side and let's see, 5 over to the other side, then that means that b is equal to negative 1. So then in conclusion, we can go ahead and plug a, b, and c back into there, and that's going to be our partial fraction, which in this case looks like it's going to be 1 divided by x minus 2, and then we have plus looks like it's negative x minus 4 all divided by x squared plus 2x plus 4. And at this point, hopefully you're going to get some sort of partial fractions, which you can then integrate because that's going to make our life a lot easier then. Okay. All right, so those are kind of like my special rules, number one in this case. Now, the other special condition is that if you have the following, okay, if you have a repeating factor of x minus a raised to the r power in the denominator, then the partial fraction would contain r number of those partial fractions. And here's what that means. So let's say you got something nasty like this guy over here. So in terms of what it breaks into for the partial fractions, you'll notice that there are two factors on the bottom. We have specifically two unique factors, I should say. We have x and also x cubed plus 1. So you'll notice on the first part, what's happening is that you have x cubed. So what that means is we're going to have three partial fractions for this one. One for x, one for x squared, and one for x cubed. Everything that leads up into x cubed then. And for the numerator, it's just going to be a, b, and c. Because that corresponds to the linear factor that we have on the bottom of x. So that's why it's just a, b, and c, and not a plus bx plus c plus c x squared and so on and so on. Okay, because our factor is just strictly x, that's why it's just a, b, and c. Whereas for the second part, because we have x cubed plus 1 quantity squared, and similarly, then that means that we have x cubed plus 1 as one of the factor, and then x cubed plus 1 squared as another factor. And in the numerator, respectively, we have dx squared plus ex plus f, because in the denominator, you have something that is cubic. And then for the second part over here, same thing. We have gx squared plus hx plus I, because the denominator over here, that part is also going to be cubic. Fortunately, we're not going to be solving for something like this for all of these coefficients because that's just going to be tedious work. But that's just to give you an idea as to what happens when you have a partial fraction that is going to be repeating then. Okay, so let's go ahead and take one of these guys right here and solve for it and apply this whole partial fraction thing so you can see how that works. So in our example over here, we have the integral of this nasty thing over here. Now, if you remember from our last video, we said the first thing you want to do is if the numerator has the same degree as the bottom or something that's higher, then that means that we have to use long division to simplify first or use some sort of cheap algebra trick. I don't see any cheap algebra tricks, so in this case, we're just going to have to use long division. So by long division, then this is what you're going to get then. So we have the numerator right here. We have the denominator over here, which I'm going to write as x cubed plus x squared plus 0x plus x, just to kind of fill in all the missing terms. So you can see by long division, which is actually pretty short for the most part, you're going to end up with this guy over here, 1 plus 3x squared plus x minus 1, all divided by x cubed plus x squared. And this is the part over here where you can then apply your partial fraction. So then that's where this next part comes in. So you can notice that I took the denominator and I factored it. And if you notice that our rule, this is where everything kicks in. Because we have x squared, then that's where we have x over here in the first one, and then x squared over here in the second one because of our second rule. So the first partial fraction is a over x, and then the second partial fraction is b over x squared, and then the third partial fraction is according to the last factor, which is x plus 1. So that's c over x plus 1. Now we're going to go ahead and multiply both top and bottom by the common denominator, which is x squared plus x plus 1. And then we have this guy that's down here on the bottom. At this point, we can go ahead and use our system of equation, first option, to solve for a, b, and c. Or we can go ahead and let x equal to certain values, so then that way we can go ahead and plug it in. I think I'm going to go ahead and choose to let x equal to certain values because that seems a lot easier. Now, if you're wondering, okay, well, is the system of equations something that we should completely disregard because it seems so difficult? And unfortunately, the answer is no, because there are some times where you can't actually solve for the partial fraction by letting x equals to certain values. It's just that much harder. It's actually a lot easier sometimes to just solve for using system of equation. Okay, but anyhow, let me just kind of show you what happens here. First, we're going to go ahead and say let x equals to 0. And then what's that going to do is that it's going to get rid of this term over here, and it's going to get rid of this term over here. So that leaves you with this term right here, which becomes just b because x is equal to 0. And here on the left, x equals 0 will give you -1. So b is equal to -1. Then the next part, let x equals to -1, just to get rid of a different factor. If you do so, the left will be equal to -1. And then on the right-hand side, you are going to get, oh, actually, no, on the left-hand side, you're going to get 1 because it's going to be 3 and then -1 -1. So yeah, it's equal to 1. And on the right-hand side, if I plug in -1, the a term and the b term cancels out. So that leaves you with only the last part, which is the cx squared. And that's where that c is actually coming from. So c is equal to 1. Now we're going to go ahead and choose another value for x, that, whatever you want at this point. So I said, okay, let's go ahead and let x equals to 1 in this case. So then if I plug into the entire equation, we get 3 is equal to 2a plus 2b plus c. And if you remember, we just saw for b and c, so that's where I'm going to go ahead and plug in for b and c. And then eventually that will allow me to solve for a. So there it is, taking my nasty integration problem, using long division to get something like this over here, and then afterwards using partial fraction to get something that's a little bit nicer than as a result. And now we can go ahead and take the antiderivative. So this is going to be our answer then. All right. So I know this video is a little bit different because normally I would go through the work with you guys, but I figure, in this case, you can probably pause and try to take a look at what part you're missing and then go from there. Okay. All right. Well, thank you so much for watching. I will see you guys next time. Take a bye.